charges balance it by charge? Because aren't there too many minuses?
No, they were balanced by charge before. We have 3 minus here and 3 minus here. These are both neutral. This is 2 minus, but that's 2 plus, so that would have canceled out. So we have 3 minus on both sides. Alicia?
Can we now take off more water?
Why not? How about if we get rid of that water and get rid of one of those? Okay? So now let's add everything together, and we have water plus 3 cyanide, plus 2 permanganate goes to form 3 cyanate plus 2 manganese 4 oxide plus 2 hydroxide. Okay? Again, let's double check mass. 2 hydrogens there, 2 hydrogens there, that's good. Oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 on that side. 3 carbons, 3 nitrogens, 2 manganese. It all balances, we're good. Okay? So once again, this is kind of a long drawn out process, but if you will do it step by step and check your work at each step. Oh, we should be balanced by charge too. What's the total charge over here? Minus 5, there's 3, 4, 5. Over here we have 3, 4, 5, balanced by charge too. So yeah, don't forget to do that, like I just did. Twice now.
Which you remembered in that sequence.
But I remembered after she reminded me.
Oh.
Yeah.
In other words, listen
on the test, you're going to have to remind yourself. Okay? You notice you remember how we talked last time about signs of a redox reaction? Yeah, that's the one. If I ever saw a permanganate ion, especially if it wasn't attached to anything, that would be my first thing that I would think. That it's probably redox. For some reason, chemistry professors love to put problems together with permanganate ion. Okay, so how about some new stuff? Yes, let's.
You seem very excited.
Well, you got 30 seconds to fix that. We're going to start chapter 14 today. We are talking specifically in chapter 14 about acids and bases. The good news is a lot of what we're going to talk about is probably going to be familiar because it's stuff that we touched on a bit at the beginning of chapter 4. We're just going to go into a little more detail. What the yachts is that? All right. So, you may recall in chapter 4, we learned 3 definitions of acids and bases. Would one of you be so kind as to tell me the name of one of those and what the definition of an acid and base were under that system? Arrhenius. Bonus points if you can spell it.
A-R-R-H-E-N-I-U-S.
Wow, I'm impressed. What is an Arrhenius acid? Produces hydrogen ion. Okay, and an Arrhenius base produces hydroxide. This is the simplest definition of an acid and base. It is also the least inclusive, and consequently probably the least useful. All right. What's the next step up?
Then we have Bronsted-Lowry.
Bronsted-Lowry.
I do not remember.
And this is Bronsted-Lowry? Okay. What is a Bronsted-Lowry acid?
It's a proton donor.
Proton donor. And what is a proton? proton is just H plus. Okay? What is a Bronsted-Lowry base? Proton acceptor. Does it have to be hydroxide? No, it does not. There are other things that will accept a proton just fine. Ammonia, for example, will accept a proton to become ammonium ion. That makes ammonia a Bronsted-Lowry base. All right. This is the version that we will use most often. Okay? The little red star right there. All right. The last version. Lewis. Who we will also talk about towards the end of this quarter. What is a Lewis acid? An electron pair acceptor. And a Lewis base?
An electron.
Electron pair donor. In other words, anything with a lone pair of electrons could qualify as a Lewis base. Because theoretically, that lone pair could be used to hook onto something else. Okay? It would be a good idea if you learned these definitions and the names associated with them, but most importantly, if you knew how this one specifically worked. And we'll touch on this one a little bit too. And if you learn Bronsted-Lowry, you'll already know Arrhenius because it's kind of a subset. Okay? Any question on that? Let's say that one you've seen before. That one shouldn't be too big a deal. All right. So, what happens when an acid dissolves in water? If we were to express this as a chemical equation, and our acid is HA. We'll frequently write acids this way. H being the hydrogen ion that all acids produce when they dissolve. A just being a generic term for whatever anion it happens to be stuck with.
Can I just say that on our homework, there was one of those, it was N, right? It was just like a genetic variable thing.
Yeah.
I spent probably 10 minutes going over the periodic table trying to find an
Just
N.
looking
and then
for
I was
M.
complaining about it at dinner, and my little 10-year-old brother was like, so kind of like a variable in math, and I'm like, that's what it is.
There you go. Okay,
Sometimes
so
that's what it takes. Like, my brother helped me with my calculus homework.
when an acid dissolves in water, what happens?
And the H plus dissolves.
Okay,
Like it
what you end up getting,
separates.
you dissolve that in water, you get H plus plus A minus. Make sense? Okay. That's one way to look at it. That's the simplest way. Now, if we're going to be a little more realistic about it, here's what really happens. Okay? Really what happens is this. So if we get whatever our acid is plus water, what we really get is potentially an equilibrium reaction that produces these two things. H3O plus A minus. Now, I think H3O plus was one of those ones that was on your study sheet. Do you remember what it's called? Hydronium. Realistically, when an acid does this, the hydrogen doesn't just float out, separately. It attaches to a water molecule, and you get a charged particle as a result.